Okay, so then hydroxide, or no, let's go carbonate ion. CO3, -2. Bicarbonate ion, HCO3. Maybe you were thinking, it's also on the flashcards, hydrogen carbonate ion. Is it? Yeah. Bicarbonate is what you'll probably see the most often. So, bicarbonate, CO3 minus. What about dichromate ion? CR2O7 -2, Cyanide ion? CN minus. Hydroxide ion? OH negative. Nitrate ion? Nitrite? NO2. Oxalate? Good. Phosphate ion? And then sulfite ion? SO3. So knowing these polyatomic ions will make Unit 2 so much easier. I know they're a lot to memorize, but once you have them, it's kind of like you're learning a foreign language. And if you don't know the key words, then it makes speaking Unit 2 very difficult. So, don't be discouraged if you made mistakes on the quiz. Better to make mistakes on the quiz than your actual exam, because the exam is worth a big part of your grade. All right, so we left off last time. We had written a lot of formulas. We'd gone through and written the formulas. We did the cross and drop. We were working on that. One of the things that I wanted you to practice was to write formulas from names. So on page 11. So we'll go over these. Make sure you got the right idea. Ammonium phosphate. What's the formula for that? NH4. That would be me. My phone went off. So NH4 and then 3 PO4. Very good. So if you didn't know your polyatomic ions, writing the formula for this would be impossible. So this is a good example of just how powerful your polyatomic ions are. What about iron 2 oxide? F plus 2, O minus 2. You do the cross and drop and you get Fe2O2. But remember, you're dealing with ionic compounds, and it's the simplest ratio of ions. So you have to simplify. So you get FeO. Now, for ionic compounds, you simplify. For covalent compounds, you do not simplify. So I'm going to start saying that. And so when we see covalent compounds and you want to simplify, ask yourself whether it's ionic or covalent. Okay. Iron 3 oxide, how do you write the formula for that? So it's iron 3, minus 2, you do the cross, you do the drop. So you get Fe2O3, good. And then lead 4 oxide is Pb plus 4, O minus 2. Do the cross and drop. Come up with Pb2O4. However, can you still simplify that? PbO2. You can divide both of these by 2. All right, calcium chloride. So CaCl2. Potassium nitrate. KNO3, because potassium is +1, nitrate is -1. Magnesium hydroxide, Mg +2, O -1. You do the cross and drop. MgOH2.
Don't you have parentheses on that?
Yes, I do need a parentheses on that. So remember, when you're dealing with polyatomic ions and you have a formula that requires more than one polyatomic ion, you have to use parentheses. If you think about what polyatomic means, many atoms. So this is an ion that is made up of many atoms. So put that parentheses around there. Aluminum sulfate, Al +3, SO4 -2. You do the cross and drop. And Al2. Good. Copper 2 sulfate. Oops. You do the cross and drop, and you'll find that you can simplify these. CuSO4. And then, let's see, lead 4 dichromate. You do the cross and drop. You get Pb2 Cr2O7 4. And notice how this formula looks very similar to number 4, lead 4 oxide. So you kind of get in the habit of recognizing these, and then simplifying them is not as difficult. So you end up with Pb Cr2O7 2. Sodium bicarbonate, Na plus HCO3 minus NaHCO3. So that's, sodium bicarbonate is baking soda. So if you were to look on the side of a box of baking soda, it would say sodium bicarbonate. Zinc nitrate. Zinc is a transition metal, but it's a transition metal that can only have one charge. So it's +2. So that's why it didn't say zinc 2 nitrate.
It was zinc. Was it zinc, silver, and what was it?
Zinc, silver, and
The long one.
yeah. Gallium, indium, cadmium. Indium. So if there's just one number written above, then you don't have to put the Roman numeral. So you do the cross and drop, and you come up with zinc nitrate, ZnNO3, 2. And then the last one, aluminum sulfite. Cross and drop, and it's AlSO3, Al2. So how did lab 8 go? Good. So I saw a lot of you comparing labs tonight and noticing that you might not have gotten the same answer. That's good. I always tell students I rarely get perfect scores on lab 8. It's kind of a challenge. Get that perfect score. But I had a student who was, in my last week, she was sure that she'd gotten a perfect score. And then she started walking around and talking to her lab partners, and she said, I missed 3. I would have, missed 3. So, it's, you almost get into little debates about, should it have a Roman numeral? Does it have it? So you go back and forth. And that's good, because you're teaching each other the nomenclature, and you're learning and you're remembering that. So it's all very good. Any questions about page 11?
Are we having a quiz on Wednesday over?
Yes, we are having a quiz. So whatever we've covered in the note packet, whatever we get to tonight, that will be on the quiz.
Tonight and whatever from the beginning.
Yes, yes,
And our next exam is next Monday.
yes. So we haven't. I know we have a. I'm gonna see how this exam goes. It might be that I bump it. No, but tonight I actually. Pause. So we'll continue on to page 12. We've been talking about ionic bonds. We've learned how to name ionic bonds. We've learned about all the polyatomic ions. So when you're talking about ionic bonds, what type of atoms typically participate in ionic bonds? Metal to non-metal. So we have metal to non-metal. Or, depending on what you're dealing with, you could have metal to polyatomic ion to polyatomic ion. So I'll put polyatomic ion, and I'll put it on this side too. So remember, with ionic bonds, atoms gain or lose electrons. So you have atoms giving up or gaining electrons. So there's a different type of bonding that goes on where electrons aren't lost or gained, they're shared. So there's something called a covalent bond, and so electrons are shared. So covalent bonds occur between non-metal to non-metal. So between non-metal to non-metal, electrons are shared. So remember, we have this octet rule. And depending on what type of atom you are, you either share electrons, or you give up electrons, or you take electrons. But it's all based on that octet rule. Everybody wants to get 8. So if you're sharing electrons, if you're one of those atoms that likes to share, you're going to try to get 8. So the following are examples of covalent bonding. When something bonds via covalent bonds, it is, instead of a compound, one unit of it is called a molecule. So I'll put that. Electrons are shared. Unit, let's see, 1 unit is called a molecule. So, water, ammonia, and methane are all molecules. And I'll show you their formulas. H2O, NH3, and then methane is CH4. We're going to draw electron dot diagrams for these molecules. But what I want you to notice is that all of these are nonmetal to nonmetal. So hydrogen is a nonmetal, oxygen is a nonmetal. Nitrogen is a nonmetal, hydrogen is a nonmetal. Methane, carbon is a nonmetal, hydrogen is a nonmetal. So that's why they bond via covalent bonds. So if you look, you're drawing the electron dot structure for water. It's made up of oxygen and 2 hydrogen atoms. The best way to go about drawing these electron dot structures is to look at the valence electrons. How many valence electrons are in oxygen? 6. How many valence electrons are in 2 hydrogen atoms? 2. So for this electron dot structure of water, you should have 8 electrons depicted. And we'll go over some more examples of this and how to draw these, but you want to start with the central atom in your electron dot structure as the one that can have more bonds. And I'll go through this coming up. But oxygen has 6 valence electrons. Does it have an octet yet? No. However, if it becomes friends with hydrogen, and hydrogen says, hey, I really like you. I want to share my electron with you. And oxygen says, hey, that's great. I can have an octet if I get 2 hydrogen friends. So now oxygen has 2, 4, 6, 8 electrons around it. Hydrogen just has 2. Remember, hydrogen is that minimalist. That's that person, you might know one that does not need anything, just very minimal. Too complicated, they lose track. So, now ammonia, again, this is nonmetal to nonmetal. Nitrogen's in the center. Nitrogen has, and I'm getting ahead of myself. How many valence electrons in nitrogen? 5. And then you have 3 from the 3 hydrogen atoms. So I'll put 2 times 1. So nitrogen just isn't quite himself when he only has 5 electrons, right? He wants to branch out, make some friends. Nitrogen will have 3 friends at a time, if that makes sense. Form 3 bonds because that gives nitrogen an octet. So if you look around nitrogen, 2, 4, 6, 8, there's an octet, and then the hydrogens have 2 around to them. So this, is kind of one of those mutually beneficial friendships if you think, you're both bringing something to the relationship. Methane. How many valence electrons in carbon? 4. What about hydrogen? Right, so there are 4 times 1, so you have 8 electrons total. Carbon's going to be your central atom. Anytime you have hydrogens in your molecular formula, they're going to be on the outside because they can only have 1 bond. Okay, good. So carbon has 4 valence electrons. Hydrogens will complete carbon's octet. So carbon likes to have 4 bonds to it. So that way you can get an octet. So how many electrons does each atom have around it? Depends on the atom, doesn't it? So 2 for hydrogen, and then 8 for oxygen, nitrogen, and carbon. All right, so then I go into water, ammonia, and methane. So H2O, NH3, and CH4 are called molecular formulas. And I mentioned this earlier. Molecular formulas versus ionic formulas. Molecular formulas are not the simplest ratio, so not at all. And we'll go through a lot of examples of these. So these molecular formulas, if you noticed, when I just wrote out the formula H2O, NH3, CH4, you didn't have any idea of how those atoms were connected until I drew an electron dot structure. So they give you an idea of how they're connected. We will see this a lot more in Unit 3 when we get into organic chemistry. You'll start to see you need a bigger picture aside from the formula. And this also ties back to Lab 8. Remember Lab 8 where you were asked to draw the electron dot structures? I don't know that yet. So you'll be able to do that by the end of tonight. All right, on the next page, I go over molecular versus ionic formulas. So it's kind of a list comparison. With molecular formulas, what types of atoms from the periodic table are involved? Is it metals or is it non-metals? Non-metals. So non-metal to non-metal. Whereas ionic formulas, what do you have? Metal to non-metal. So this is the key thing to look out for. If you have metal to non-metal, that's ionic, you simplify these. Non-metal to non-metal, do not simplify. So that is the biggest difference and point that I'm going to try to reiterate over and over again. Because I get a lot of students who say, oh, well, I can simplify. I'll give an example. In 204, I can simplify that formula. Because it has a 2 and a 4, it's divisible by 2. That would be so nice. But pay attention to the atoms. Nitrogen is a non-metal. Oxygen is a absolute. So you cannot simplify it. Now, if you were given something like Pb2O4, you have a metal and a non-metal. Yes, simplify this. Okay. So on the exam, covalent compounds and ionic compounds will be all mixed together. So it's not going to be separated. So you really need to get into the habit of recognizing what an ionic compound is and what a covalent compound is. But I'll give you lots of practice and kind of teach you ways to recognize, classify ionic covalent first.
So is the reason that they don't simplify on a non-metal is so you can kind of visualize how that molecule is constructed as we get to organic.
Right, and so with the molecular formulas of the covalent compounds, if you simplify it, you're changing how many electrons are shared, which I think is what you were getting at. So if you simplify that, then there might be an atom that doesn't have 8 electrons or 2 electrons, depending on what's involved. You're welcome. Now, I have a little table of these bonding patterns. When, I'm giving an example of an element in that group. That applies for that whole group, so you can extend that. So carbon is in group what? 4. What would carbon's electron dot structure look like? Good. Now, the number of bonds that carbon will have is that to achieve an octet. So in order to achieve an octet, how many bonds will carbon form? 4. So the number of bonds for carbon is 4. And when we get to organic chemistry, and I think I heard this when I was taking organic chemistry, if you can count to 4, you can do organic chemistry. I think it's kind of an oversimplification, but there is a lot of truth in it. When you're drawing out these structures, you need to make sure that you have 4 bonds to carbon. And, I always joke with students when I look at their structures for organic chemistry, and that's 5 bonds to carbon. There's an alarm that goes off when you have too many bonds to carbon. So, if you can also think about that alarm is going off, when you go through these elements and you have too many or too few, the same kind of thing is going on because they're not getting an octet. Now, nitrogen, what group is nitrogen in? Okay, so the electron dot structure, what does it look like? Good, so 2 on one side. It doesn't matter which side. It can be the top, bottom, left, or right. And then you have 3 unpaired electrons. How many bonds will nitrogen form? 3. So carbon, you look, it's in group number 4. It forms 4 bonds. Nitrogen is in group number 5. You think, that forms 5 bonds. But that's not true. So just, if you're ever confused, just draw out the electron dot structure. And, you can, it has
So
3 spots.
I don't know if it's safe to say, but from that pattern, do they always equal 8?
Yes. Yeah. 5 plus 3, 8. 4 plus 4, 8. Yes. Good. Oxygen, group number 6. The dot structure for oxygen, 2 groups are paired, 2 electrons paired, 2 electrons unpaired. So then the number of bonds would be 2. Now I have X as for any halogen. So this is fluorine, chlorine, bromine, or iodide. What group number is that? 7. And so I'm going to use a generic electron dot structure. I'm just going to use X. And so I'll have 7 dots on this. How many bonds would your halogen form? 1. Good. So 7 plus 1 gives you 8. Now hydrogen, what group number is it in? 1. The electron dot structure, what would it look like? How many bonds will hydrogen have? Careful. Remember, hydrogen is a minimalist. Just 1. If you remember, the noble gas that hydrogen is trying to aspire to be is helium. So helium just has 2 valence electrons. So hydrogen and helium are the minimalists. So, for your total, Jerry, the 1 plus 1 equals 2. So 2, 8, 8, 8, 8.
So this is probably dumb, maybe unrelated, but correlated. So when you had like an H3, and you had ammonium, and then you have H2O, and they're both balanced as far as their valence electrons. So you automatically think, well, both chemicals or whatever are going to be neutral or whatnot. But ammonium is harmful in humans, and is that because everything that falls down that group, as the arsenic, is that because nitrogen's just it's the nitrogen? I mean, it's not really the hydrogen.
It depends. So much of it is once you combine these atoms together, how they're going to interact. And the ammonia is very wreaks havoc on your respiratory system. But it just depends on the chemical properties of whatever is made. So kind of hard to generalize. Right. There are when we get into organic chemistry, you'll see like the halogens, and they're used a lot in anesthesia, where you have a few carbons and then a lot of fluorines or chlorines. They kind of behave similarly.
Okay.
So we'll talk about those when we get into that. Alright. Diatomic elements. These are special class of elements that if you say you call Aldrich up. Aldrich is a chemical supply company, or Fisher, and you say, I want to buy fluorine. You say, okay, here's fluorine, I'll ship it off to you. And you think that you're just going to get fluorine F. Fluorine is only found in nature as a diatomic element. So what I mean, di, two atoms occurring naturally together. So two atoms. So, for example, if I ordered, I say that. So instead of getting F, I would get F2. So, I'd call a company and say, this is not what I ordered, I just wanted F. Say, that does not exist. You cannot just get F. You can only buy it as F2. There are a few elements that only exist as diatomic elements. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So when you go to order them, or when you speak with other chemists or scientists and you say, fluorine gas was reacted with this gas, it is assumed that fluorine is F2. So that is the secret of these atoms. So it's important that you know which elements form diatomic elements. The best way I've been able to teach students is by using Hofbrinkel, Hofbrincl. So, make sure you capitalize the correct ones so that you know which elements are which. But I've had students write Hofbrinkel at the top of their exams or quizzes, so that when I say fluorine, provide the molecular formula for fluorine, you don't put just F, you put F2. So on lab number 8, there is a diatomic element on the back page. So on the next page,
So does that mean you have like two F's and it would be F and then two dots?
so we're getting ready to draw fluorine. So on page 14, I have draw the electron dot structure for fluorine. Remember, fluorine is a diatomic element, so it's F2. So I walk you through a general method for drawing electron dot structures, and this will be helpful for lab number 8. The first thing you want to do is find the total number of valence electrons of all the atoms in the molecule. So you're dealing with F2. That, if you look, how many valence electrons are in fluorine? 7. Excellent. So you have 7 valence electrons, and then you have 2 atoms. So in this electron dot structure for fluorine, you will have 14 total electrons shown. So the connected atoms in this molecule are just the fluorine. So if you want, you could, when you're first starting out, you can always just draw your 2 fluorines. And they're lonely, they want friends, they want to make that octet. So if you want, it's easy to see how they kind of click together. Like that Lego clicking, right? After you get used to doing these, you're going to be much better at predicting what atoms are on the inside, what are on the outside. Do some practice problems to reinforce that. But in some electron dot structures, a line is drawn between the 2 atoms that are sharing electrons. This line is equal to 2 electrons. So when you're counting up your electrons, you don't say, wait, I'm short. You're not short, you just have it depicted differently. So step 3, add lone pair electrons to each peripheral atom except hydrogen, connected to the central atom so that each gets an octet. What does that mean? Lone pair electrons are electrons that aren't actively participating in the bond. So these are electrons that wouldn't be denoted by a line, but rather just as dots above or below to the left or right. So for this electron dot structure, I need to give this fluorine 2, 4, 6, 8 electrons. So it has an octet. I need to do the same thing to this other atom over here. So now it's important to keep your electron accounting straight. You have count up all your electrons. You cannot have more than 14 electrons in your electron dot structure. If you have more than that, you spent too many electrons. You're an electron debt. I don't know what happens when you get a red mark on your page. All right, so 2, 4, 6, 8, 10, 12, 14. So we're good. We're on budget. So step 4, place all remaining electrons on the central atom. That doesn't apply to this molecule because we don't have any extra. We've placed all the electrons. Each atom has an octet. Okay, so on the next page, I have some practice problems. And